All right. Hello, IB students. Um, Hope you all had a nice weekend. Sorry I'm a bit late starting my lessons today. I got into a conversation with my neighbor, and my neighbor just wouldn't stop talking. So that sucked up a lot of time. All right. So what we're going to do today is we're going to continue talking about the standard model of particle physics. Okay, so just to remind you, we group particles like so. Happy Monday, spicy pepper. So there was a group of particles called the quarks, and there were 6 of them: up, down, charm, strange, top, and bottom. And everything in this top row has a charge of plus 2/3, and then the mass increases that way. Then there were 6 more particles called leptons. Hey, Akshay. And the leptons, the top row had a charge of -1, and the bottom row had a charge of 0. And they are the electron, the muon, and the tau. And then there was the electron neutrino, the muon neutrino, and the tau neutrino. Okay. These particles interact by via what are called force carriers, and there's a number of force carriers. There's the gluon. There is the gluon is the force, which is the force carrier for the electromagnetic force. There is the W boson, which is one of the force carriers for the weak force. There is the Z boson, which is one of the force carriers for the weak force. And then there's the graviton. But actually the graviton, which carries the gravitational force, is the thing about the graviton is it hasn't been observed before. Okay. And then there's one additional particle which is off to the side, and it's called the Higgs. And the Higgs gives particles mass. Okay. So it's through interacting with the Higgs that particles have mass. So what are the electric charges of the force carriers? You have Q equals 0, Q equals 0, Q equals +1 for the W boson, and Q equals 0 for the Z boson. Q also equals 0 for the Higgs. Delightful. All particles with charge have antiparticles with the opposite charge. So the and those are written with a bar. So, for example, an anti-electron would be written as E bar. It would have a charge of +1. An anti-muon would be muon mu bar. It would have a charge of +1. An anti-down down has a charge of -1/3, so an anti-down has a charge of +1/3, etc. Okay. Oftentimes, with the weak, the W boson, it has an antiparticle. You can see because it has charge, and typically the actual W boson is called W plus, and then its antiparticle is called W minus. But that's only for the weak force carrier, the W boson. Okay, so all of these particles, even the ones with charge 0, have antiparticles. Okay, so there's an there's an anti-neutrino, for example. Okay. So today what we're going to talk about is particle interactions. Okay. And it turns out that particles interact by spitting out force carriers. So all particles can spit out force carriers. Okay. So let's talk about the electromagnetic force, for example. So we're gonna draw pictures of the interactions of particles using what are called Fineman diagrams. So a Fineman diagram is a picture of the interaction of particles. Okay, and when we draw a Fineman diagram, we're gonna imagine time as running from. Let me get this piece of paper. We're going to imagine time as running horizontally. And we're going to imagine space as running vertically. Okay. So let me show you what a Feynman diagram might look like. This is an example of a Feynman diagram. So what we have here, and you're going to label all of the particles. Okay. So maybe this is an electron. And then what comes out is an electron. Okay. And then this wavy line represents a photon. Okay. So basically, the electron spits out a photon like that. And then the electron and the photon are separating from each other as time goes on. Okay. So that's called a Feynman diagram. The diagram is just a sort of a schematic representation of the interaction. So if you wanted to draw it like this, that's perfectly fine. You know, it doesn't really matter the details of how you draw it. As long as you have basically all Feynman diagrams, they have one arrow going into. This is called a vertex, by the way. So this right here is called a vertex. So any vertex that is a Feynman diagram is going to have one arrow going in, one arrow going out, and a force carrier. Okay? So as long as you have those three, it's going to make sense. Okay? So anything that has electric charge can either can spit out a force carrier. So for example, a charm quark could have one of these diagrams as well. A charm quark could spit out a photon. Akshay has a question. As a photon is spit out, it spits out light. Yes, that is correct. They do spit out light. Do the other force carriers spit out a property? Well, you have to think about light is a particle. A photon is a particle of light. So, it's not so much a property that they're spitting out as a thing that they're spitting out. They're spitting out a force carrier. So this could be an up quark, for example. All right. Now, one of the things we can do with a vertex, okay? One of the things we can do with a vertex is we can take the original vertex. So I'm going to take this one, and I can bend the parts of the vertex around. So for example, what if I did this? What if this is an electron and this is an electron and that's a photon? So is this still a valid vertex? Yes, it is, because it has one arrow going in, one arrow going out, and a force carrier. But here the force carrier comes in and hits the electron. So this is the emission of a force carrier. This is the absorption of a force carrier. Okay. Furthermore, we could imagine taking the vertex and doing something like this. We can twist it all different ways, but it always has one arrow going in and one arrow going out. Okay. And so this would be an example of maybe an electron. Now notice how this arrow goes with the direction of time. And this arrow, because this arrow is going to the right, time is flowing to the right. This arrow is going more to the left. So that's against the arrow of time. And any arrow that goes against time is an antiparticle. So this would be an anti-electron. Okay. So that's an anti-electron, and this is a photon. So this represents an electron and an anti-electron colliding with each other and transforming into a photon. But notice how it's the same. It's the same idea of the vertex. It has one arrow going in, one arrow going out, and a force carrier. Okay. So I could draw it a different way, some different things. So this is also a valid vertex. See how this has one arrow going in, one arrow going out, and a force carrier, okay? But this arrow is going against time, so that must be an antiparticle. That's an anti-electron, for example. Or this is and then this would be an anti-electron, and that would be a photon. So that's an anti-electron spits out a photon. Okay. So these are the vertices. We can kind of play around with bending the different the three legs of the vertex around to make different things. Then what we can start to do is we can start to chain them together. So let me show you a Fineman diagram. Maybe a Fineman diagram looks like this. Okay. So maybe this is an electron. Maybe this is an up quark, for example. Actually, this would be an anti-up quark, because see how this arrow is going against time. Okay, so so notice how each vertex, we have two vertices here, there and there, and each vertex obeys the rule of the vertex. it has one arrow in, one arrow out, and a force carrier. One arrow in, one arrow out, and a force carrier. It's just they're linked together via the force carrier. Okay, so that's a photon. This is an electron. This is an anti-up quark. Okay, so this would be an example of what is called electron anti-up quark scattering. So scattering is anytime two things bounce off each other, essentially. Now, how are they bouncing off each other? They're bouncing off each other by emitting a photon. Okay, so in this case, the electron emitted a photon, and when it emitted the photon, it kind of recoiled. And then that photon hit the anti-up quark and caused it to recoil. All right, so that's an example of scattering. What if I redrew the diagram like this? So it doesn't matter really which comes first. So in this diagram, the electron emitted the photon. And in this diagram, the electron absorbs the photon, you see. Notice how this arrow, I was sneaky. This arrow is now going with the direction of time. So that's a particle. So this would be an up, maybe an up quark. So this would be electron up quark scattering. Okay. So I'm going to draw some other ones that are more interesting. Maybe I'll draw a Fineman diagram that looks like this. Okay. So here's a photon. Let's make this an electron. Notice how each vertex here, again, has one arrow in, one arrow out, and a force carrier. So then this would be an anti-electron. And then let's say that this is a charm quark, and then this would be an anti-charm quark. Notice how with the electromagnetic force for the vertex, these two particles have to be of the same type. So one of them could be an anti if the arrow is bent backwards, but you have the same type, and then you have a force carrier. Okay, so what do we have here? We have an electron and an anti-electron come together. They transform into a force carrier, and then the force carrier splits up into a charm quark and an anti-charm quark. So this type of diagram I would call pair transformation. You have a pair of a particle and an antiparticle transforming into something else. Okay, so the identity of the particle itself is transforming. It's pretty cool. Notice how you can only do that with particles and antiparticles. I could draw some other diagrams for you. Let's draw one that looks like this. Okay. Yeah. Okay, so this is a photon. Let's say that this is a top quark, and that's a top quark, and that's a photon. So what do we have here? We have a top quark, spits out a photon, and then later on it absorbs a photon like that. So this is a photon, and top quark basically bouncing off of each other. Okay, so this is called top quark photon scattering. Okay. Here's another one. It's kind of cool. I like this one a lot. So this is a particle because the arrow goes with time. But notice here it's an antiparticle. So this is an anti-electron, photon, photon. So notice how we have an electron and an anti-electron go in and two photons come out. Okay, so this is two particles hitting each other and transforming into photons. So this is called pair annihilation. And in pair annihilation, you basically have particles becoming pure energy. Okay, but it still obeys all of the rules of Fineman diagrams. And so we could also draw this going the other direction, where we have like that. So here, notice how this obeys all the rules. Each vertex has a force carrier, arrow in, arrow out. This vertex has a force carrier, arrow in, arrow out. So this obeys all the rules. And for this one, you have photons coming in and a particle and an antiparticle coming out. So this is called pair production. Okay. Any diagram that you can draw that obeys these rules of force carrier, arrow in, arrow out, any diagram that obeys the rules like that is something that can actually happen in nature. Okay? That's what's really cool. So you could literally, this is two photons become particles. So what this means is that you could take two laser beams, which are basically photon guns, and shine them at each other. And there's a possibility that if two photons smack into each other, you could get electrons and anti-electrons popping out of that. It's crazy, but it can really happen. Now, going back to this, anything with electric charge can spit out or absorb a photon. So quarks can, and the top row of leptons can. Neutrinos cannot because they have zero charge. Also, the W boson cannot because force carriers can't do that. Okay, so of the particles, or of the quarks and leptons, everything except for the neutrino can spit out a photon or absorb a photon. I think I just swallowed a fly. Little protein. There's another force carrier. It is called a gluon, which is for the strong force. And in Fineman diagrams, gluons are drawn as curly lines. Okay? Curly Q lines, like a spring. Now, the thing with gluons is gluons can only be emitted or absorbed by quarks, because only quarks feel the strong force. Okay? So you could have a vertex that looks like this. You have up quark, and a gluon comes out. So this is a yes. But a no would be an electron spits out a gluon. Why is that? Because an electron is not a quark, okay? An electron is what's called a lepton. So many of these diagrams are also possible with quarks, or with gluons, for example. So for example, you could have something like this. This would be maybe this is an up quark, maybe this is a down quark. Okay, so right here, I have electron up quark scattering by exchanging a photon. This would be up quark, down quark scattering via a gluon. Okay, so notice how we couldn't do electron up quark scattering via a gluon because the electron can't absorb gluons. All right. So at any rate, this lesson is going a little bit long. I didn't get to everything that I want to get to. So one of the daily items today, you're not going to be able to do. It's drawing the Fineman diagram for the weak force. So I'll talk about the Fineman diagrams for the weak force tomorrow. And then so we'll be talking more about this tomorrow. All right. Thank you for watching. I hope that made sense. Students find this particularly difficult. So I don't know why, but they do. So please, there's tons of videos online explaining Fineman diagrams. This is the term you want to look up, Fineman diagram. So check it out. Thank you for watching, and I hope you have a nice rest of the day. Bye.